All right, let's get this magnetic force party started. The statement reads, for part A, find the force on a square loop placed as shown in figure A, near an infinite straight wire. Both the loop and the wire carry a steady current I. B, find the force on a triangular loop in figure B. A review of the figure in question shows that for part A we have an infinite wire on the bottom and separated by a distance S is the square loop, both carrying current I. For figure B we have the same scenario except the triangular loop of side length A, all again with both current I separated by a distance S. Things to know for this problem: the field of a line, clearly, and then we have segments of lines that we can chop this up into, and the force, or at least the magnitude. The force is equal to the current times the integral of the cross product of the differential line element with the magnetic field. Before we get started with any analytic solution, let's first draw out the scenario with the square loop and the magnetic field coming from the loop and then the line. You'll see in this diagram I made, I kind of color coordinated things to make it easier. We know that the separation distance from the bottom part of the loop is S, and then the top part of the loop is S plus A because the length is A. Let's also note that in the blue case that 0 to A runs from left to right following the current. So we're going to keep that same attitude when approaching the top loop, 0 to A, in the same consistency. And then if we look, we know that from the right-hand rule, the current on the top part of the loop runs into the page, as denoted by the purple X's, and the magnetic field from the bottom current is coming out of the page with respect to that bottom wire. That bottom wire itself, pointing in the right direction, leads to a magnetic field coming out of the page onto the loop itself. And so that just helps us with our directionality, which we'll need in the cross product result itself. All right, so for the analytic part of the solution, for this first scenario A, the force on the vertical components cancel, which is why I didn't draw anything on the diagram. Again, that's just a symmetry argument. You can use that just like we did in electrostatics. The bottom line segment has a magnitude of the force bottom is equal to I, integrated from 0 to A, because that's the length of the loop, of dl cross B. We know that since we have a cross product, we need to take into account just the directions, which is why we drew the diagram to help you identify them. And we see that we have the magnitude of the magnetic field that comes out of the cross product and the magnitude of the differential line element, dl. But we know that dl is running from right to left, so that arrow points left, and the magnetic field is pointing out of the page. So left times out, again, according to the right-hand rule, leads us to a direction of up. And that's how we get the up arrow in the integral. And then the integral is just of the line segment, so we know that that's A minus 0, which is A. So that's how we get this force bottom is equal to mu naught I squared, because we have the I from the B field and the I from the force formula, times A all over 2 pi s, since that's our separation distance, with the up arrow. If we do that same argument for the top segment, we have that we have the down arrow, or the line segment running from right to left, leaving us with the left arrow, and then we have that the field goes into the page. So again, according to the right-hand rule, that would result in a downward-facing arrow. That's what we see here. The only difference is that instead of S in the denominator, we have S plus A due to the increase of height due to the square length itself. But we know from superposition that the force is equal to the net force is the vector sum, and so we can just add them together. And that's what we do here. So we're going to have to figure out a way to simplify in a manner that encapsulates the proper direction of this, or the proposed direction. We don't know the field strength, things of that nature, but based on this geometry, we know that we can factor out a mu naught I squared over times A over 2 pi, leaving us with 1 over S in the up direction plus a 1 over S plus A in the down direction. If you see my little note below, we know that S is less than S plus A, and both of these things are real values that are positive since they're distances. So if we take their inverse, then the greater than sign flips, and we know that 1 over S is greater than 1 over S plus A. That tells us that the magnitude of the force pointing up is greater than the magnitude of the force pointing down. So our net result should be pointing up. So I go ahead and flip the sign on the second fraction to a minus sign, but I also flip the direction to up. So doing that allows us to combine these things with keeping the directionality consistent. So we find a common denominator in the next step. The s's cancel, leaving us with the factor of a in the numerator. And that's how we get mu naught I squared a squared over 2 pi s times s plus a, pointing in the up direction. Similarly, we'll have to take this approach and apply it to the configuration in B. So let's look at that. With this being a triangle, the symmetry only works in one place. We draw on the bottom part of the triangle, the bottom leg, a vertical up at A divided by 2, and we see that we have a mirror image. That only happens vertically. Horizontally, if we did that, we would not have a mirror image, so we're going to have to take that into account. We see that we're going to have a recurrent relationship here with the s over square root 3, because that's just an intrinsic property of the ratios of the triangle. It being an equilateral triangle, each angle measures 60 degrees, and if we take the tangent of 60 degrees, that leads us with this thing. And I'll dive into the analytics of that, but I just want to show you that the separation distance S leads a direction to the end of the triangle of S over square root 3, given that this is our coordinate system. So in words, the bottom segment is the same as part A, nothing new there. The two sides that are at an angle require more work. The geometry has a symmetry about the vertical center of the loop, which I just described, about A equal 2, but not horizontally. So we'll need to split this up and find the proper domains for the integral that we just had in the last part. And the diagram shows that tangent of theta is equal to s over x. Solving for x leads us with this. You will see this again in a couple spots. But that's important so we know where to integrate from, to and from, with respect to the x direction. Alright, so on the left side, we know that the b of that line is just mu naught I 2 pi y in the z hat direction. We haven't defined what y is in this case, so we'll save that for later. But we can take care of the cross product. We should know the directions now. With dl going in all three coordinate directions, since we set up a coordinate there, we know that in the b field occurring only in the z direction, that the cross product is pretty simple. All we get is b dy x hat minus b dx y hat, because everything else is 0, and a cancellation happens. Again, we can factor the magnitude of y out, leaving us with mu naught I squared over 2 pi y times dy x hat minus dx y hat. But again, since our geometry tells us that we have a symmetry about the vertical line, or vertical center, we know that the x directions cancel, so that dy term is not something we need to worry about when integrating. As we saw how we set up the triangle in the diagram, we can apply that same argument for what y equals, which is just square root 3 times x, again from tangent of 60 degrees. Putting this all together now, the force of the left and the right sides is thus 4 sides equals 2, since there's 2 sides. Notice that our left point of the triangle in the dx direction, or not even dx direction, but the dx length, starts at s over square root 3, because we don't know where in space it is, so we just take s and put it at that coordinate point. And then we know that we have to add all the way up. Since we're doubling it, we're only going to the midpoint of the triangle, which is s over square root 3 plus a over 2. So thank you, symmetry, for that. But again, we see here that we're just taking the magnetic field magnitude, mu naught I squared over 2 pi square root 3 x times the results of that cross product cancellation terms of the x hat direction. And that this leaves us with negative dx y hat. So pretty much everything except the 1 over x is a constant, so we kick it out to the left. The negative 2 for the direction and the two sides. And then we have 1 over x dx in the y hat direction. That's a simple ln integral. Again, since all these are real and positive, we don't need to worry about the absolute value here. Again, this substitute in after, evaluate it. Notice that with the rule of logs, the minus sign allows us to divide it. And if we split up the fraction, that gives us s over square root 3 over s square root 3 plus a over 2 divided by s square root 3. So the first term in that separation goes to 1, which is what we see here. And then anytime you're dividing by a fraction, you multiply by the reciprocal, and that's how we get the square root in the numerator and the 2 in the denominator with the s. Again, all in the y direction. Since this is a vector sum and we're pointing upwards with both of these results, we just add them together. They both have a common factor of mu naught I squared divided by 2 pi. From the bottom segment, that just leaves an inside factor of a over s. And then we have 2 copies of 1 over square root 3 ln 1 plus root 3a over 2s, again, all in the up direction.